Okay, so before we start this example, we only have one example today, but it's a long example. Before we start, I want to go ahead and just talk about each test, so it's very clear what we're looking for in each test. Okay. Test number 1 is we have the first derivative test. Okay. With the first derivative test, I first need to find the first derivative, set it equal to 0, and get my critical numbers, right? Once I have my critical numbers, we look at the intervals of increasing or decreasing, right? That's what we're looking at, is intervals of increasing or decreasing. So I need to pick some test values to plug into my first derivative, okay? I look at my intervals, pick some test values, plug them into my first derivative. And I'm either going to get a positive or a negative output. What are those positive and negative outputs telling me about my function? If I'm plugging it into the first derivative, what information am I getting? Increasing or decreasing. Okay, so I'm getting information about increasing or decreasing. And I'm using that first derivative test ultimately to determine if my critical number is a relative max or a relative min, right? That's the whole point of doing the first derivative test. I'm looking for intervals of increasing or decreasing so that I know my max or my min, okay? Then we have the second derivative test. So in the warm-up, we did the second derivative test. What's the whole point of the second derivative test? Again, it's to determine if you have a relative max or min. Okay, it's just the way we go about it is a little bit different. I'm going to figure out what my critical numbers are, right? Where do I plug in those critical numbers? Into the second derivative, right? My second derivative is going to tell me what about the function? Concavity, yep. And then based on the concavity, that's going to determine whether my critical numbers are a relative max or a relative min, right? So that's the second derivative test. Okay. Then I have what's called a concavity test, and that was the second part of the warm-up we did today. So for the concavity test, that has to do with points of inflection. Okay? So anytime you see a chart for concavity test, we're referencing the points of inflection. So this time I need to find the possible points of inflection. Right? I find the possible points of inflection, and then I set up my intervals. Right? I pick test values for my intervals, and where do I plug in those test values? Second derivative, right? And what's my second derivative going to tell me? Concavity, right? Anytime I plug into the second derivative, it tells me concavity. And ultimately, that's going to tell me where my points of inflection are, where my actual points of inflection are. Okay, so we've got 3 different tests that we've talked about so far. I just wanted to recap what each test was and what the purpose of the test is. Like, what am I trying to find by using these tests? Okay. So my learning target today is to use the second derivative test, the first derivative test if needed, right? I only need that if the second derivative test fails, and the concavity test to sketch a graph of the function. Okay? So it says for the function, find the relative extrema using the second derivative test, if possible. State the coordinates of the points of inflection, find the intercepts, and sketch the graph. Let's take care of intercepts first, because if I don't do it at the beginning, I will forget to do it at the end. So let's do that first. Let's find our y-intercept. With y-intercept, I plug in 0 for x, right? And I have to solve for y. So if I plug in 0 for x here, what am I going to get? 0 minus 1 squared. That's just going to be 1. And here I have 0 minus 3. Negative 3, right? So 1 times negative 3 is just negative 3. X-intercept, where do I plug in 0? I plug in 0 for y. Right? Pause this. Okay. So So for x-intercept, we replace y with 0, right? So it's going to be 0 equals x minus 1 squared times x minus 3. So what do I get for x? If I set each factor equal to 0 and solve, Jordan? Actually, right, if this is x minus, this is like x minus 1, x minus 1, x minus 3, like this, right? So really I just get 1 with a multiplicity of 2, right? So good, but yeah, I'm going to get 1 and 3. Very good. Okay. Actually, if you remember, you're going to see a bounce at 1 if it's an even multiplicity. So I don't know if you remember that from Algebra 2. But. All right, so I get my x-intercepts are 1, 0, and 3, 0. Okay, so I've got a y-intercept at 0, -3. I've got a x-intercept at 1, 0, and I have an x-intercept at 3, 0. Okay. Any questions on finding your x or y intercepts? Okay, so now let's go ahead and get into the tests. First, I'm going to use the second derivative test to figure out your relative maxes or mins. Okay, so let's go ahead and first find the first derivative. Okay, I need the product rule here. So I'm going to take the derivative of the first. So that's going to be 2 times x minus 1 times 1, but I don't need to write that in. Derivative of the first times the second. So the second would just be x minus 3 plus the first, x minus 1 squared, times the derivative of the second. The derivative of x minus 3 is just 1. Okay, so I'm not going to write in times 1. It's really not necessary. Okay. So with the first derivative, just to clean this up a little bit, I'm going to factor out a GCF. What do both terms share in common? Mallory, what would you factor out as the GCF here? What do they both have in common, both of these terms? X minus 1. So I'm going to factor out an x minus 1. And then let's see what's left. If I factor out an x minus 1 from this first term, I'm going to be left with a 2 and an x minus 3. And if I factor out an x minus 1 from this term, I'm just going to be left with x minus 1. Okay. So let's see, cleaning that up, I get x minus 1 times, this would be 2x minus 6 plus x minus 1. Or that would be 3x minus 7 in that parentheses. Any questions about that? So if I set my first derivative equal to 0 to find my critical numbers, I'm going to end up with critical numbers 1 and 7/3. Right, if I set each of those factors equal to 0 and solve. Any questions about how I got my critical numbers? Okay, so for the second derivative test, I'm going to find my critical numbers, and then I'm going to plug my critical numbers into my second derivative. Okay, so down here in my chart, I'm going to use the critical numbers 1 and 7/3, and I'm going to plug them into my second derivative. Right? So I need to know what my second derivative is in order to plug them into my second derivative. So now let's go ahead and find the second derivative, f double prime. So here's my first derivative. Again, I'll have to use the product rule. So second derivative, we take the derivative of the first times the second, so times 3x minus 1, plus the first, which is just x minus 1, times the derivative of the second, which would be 3. Any questions about how I use the product rule for that? Cleaning this up, my second derivative is 3x minus 7 plus, this would be distributed through to both terms, 3x minus 3. So So I get my second derivative is 6x minus 10. Any questions about that? Is that okay? All right, so now that I know what my second derivative is, let's plug in each critical number into the second derivative. So if I plug in 1 into the second derivative, I'm going to end up with 6 minus 10, right? That's a negative value. If I plug in 7/3 into my second derivative, we're going to have 6 times 7/3 minus 10. So I get 4. So that's going to be a positive value. Okay. All right. So here I've got a negative value in my second derivative. Does that make 1 a max or a min? Jaspreet, what do you think? If we get a negative value in our second derivative, would that make 1 a max or a min? It would be a max, right? Negative means that we have concave down, so that would make 1 a max. Good. Okay. And if I plug in 7/3 and I get a positive value, Allie, would that make 7/3 a max or a min? Min. Good. That's going to be concave up, so here I'll have a min. Okay. Any questions about that? All right, so we just determined that we have a relative max at 1 comma something, and we have a relative min at 7/3 comma something. How do I get my y values for the max and the mins? Abby, where would I plug in 1 and 7/3? Good, into the original equation here, original function. So I'm going to plug in 1 into my original function. So I'm going to have parentheses 1 minus 1 squared times 1 minus 3. Right? So I end up with 0. Okay, so I have a relative max at 0. And then I'm also going to plug in 7/3 into my original function. So I'm going to have 7/3 minus 1 squared times 7/3 minus 3. So I get this crazy decimal, and I'm going to math bracket. So I'm going to hit the math button and convert it into a fraction. So I get negative 32 over 27, which I'm going to just note this. It's about negative 1.2 approximately. Okay, because ultimately I'm going to be graphing this later. So negative 32 over 27 is an exact point, or an exact value for that point. But when I go to graph it, it's not going to help me much. So it's nice to just take note that that's about negative 1.2. All right, so I have my relative max and relative min. Then I have to do the concavity test. Remember, concavity test is to find points of inflection. Okay? So whenever I do my concavity test, I first need to find the possible points of inflection. How do I find possible points of inflection? Corey, what do you use to find possible points of inflection? Great, set the second derivative equal to 0. So I've already got what my second derivative is. So to get the possible points of inflection, I'm going to set my second derivative equal to 0. Okay. So I'm going to end up getting 10 over 6 for x, or see, divided by 2, that would be 5 over 3 for x. So that's my possible point of inflection. Okay. When I do that concavity test, I need to look at both sides of 5/3. So I'm going to have my possible point of inflection as 5/3. So I'm going to be looking at negative infinity to 5/3 and 5/3 to infinity. Any questions about that? So what we're doing now is we're picking a test value to plug into the second derivative, right? All right, let's see. What do I want to pick on? Cassie, give me a test value for the first interval.
0.
Sure, 0 works for me. Okay, you can use 0 in that first, for that first test value. Okay, let's see. Who else haven't I really talked to? Mallory, give me a test value for the second interval. 2. Sure. All right, so I pick my test values and I plug them into the second derivative. So if I plug, remember my second derivative, just a reminder, is 6x minus 10. So if I plug in 0 into that second derivative, 6 minus 10 is a negative. Plug in 2 into that second derivative, that would be 12 minus 10, so that's going to be a positive. Okay. So Max, if my interval here, if I plug in 0 as my test value and I get a negative, does that mean concave up or concave down? Concave down, great. And then here if I get a positive output, what would that tell me? Concave up, very good. So because my concavity changes, I go from being concave down to concave up. Am I going to have a point of inflection here? Yes. Okay, when the concavity changes, that does mean that you have a point of inflection. So I'm going to take note of that just back over here. I'm going to say that I have an actual point of inflection at 5/3, comma. Where do I plug 5/3 in? The original, right? So I'm going to have parentheses 5/3 minus 1 squared, right? Times, what is that? 5/3 minus 3. So I get a crazy decimal. I'm just going to take note of what that decimal is, negative 0.6 approximately. But I'm going to math bracket to get an exact answer. So we get negative 16 over 27 is the exact y value. Okay. Any questions about that? Just a comment. Down here for the concavity test, you're picking numbers to plug into your second derivative. Didn't I pick numbers already to plug into the second derivative up here? Would 1 have worked for this interval, negative infinity to 5/3? Yes, 1 would have worked. Would 7/3 have worked for this interval, 5/3 to infinity? Yes. So sometimes it's a good idea to strategically pick your critical numbers as your test values for your concavity test, because then you have less work to do. Here it wasn't a big deal because the second derivative was 6x minus 10. It was a really easy second derivative to plug into. But when you have more complex second derivatives, if you've already done the work the first time, don't make more work for yourself. You know what I mean? Okay, so that's just a good thing to keep in mind. All right, let's go ahead and graph this. All right, so on our graph, we've already graphed our intercepts. I'm going to graph my max at 1, 0. We already have that graph, so I'm just going to say that this is supposed to be my max. My min is at 7/3, negative 1.2. Let's see, 7/3 is about 2.3. So I'm going to do 2.3 and then negative 1.2. So this is going to be my min. I like to just label it on my graph. It makes it easier for me to graph it. And then my point of inflection is at 5/3, negative 0.6, right? 5/3 is 1.7 approximately. So I'm going to do 1.7 and then negative 0.6. So that's like right here. Okay, so that's my point of inflection. Okay, so on the left side of the point of inflection, what's the concavity? On the left side of the point of inflection, it should be concave down, right? And then on the right side of the point of inflection, it should be concave up. Okay, so on the left side here, it's going to be concave down. Make sure that you draw it through the points that you're supposed to draw it through. Okay, and then I get to my point of inflection here, and then my graph changes to being concave up, right? So now I'm changing that curve. So it's going to look like this. Any questions about that? How to graph it? So the whole point of the test is to be able to do this with no graphing calculator. Okay, so on your homework, I want you to try to do it with no graphing calculator, but at the end, it's smart to just, after you've done the problem with no calculator, check your work calculator if you did it right. So in your y1, I would put in x minus 1 squared and x minus 3. Graph it. See if it looks right. Okay, that looks right. You can even do second calculate a value at 1. There's your 0.10. Second calculate a value at 7/3. There's your point negative 1.185. Okay, or negative 1.2 is what we approximated it to be. Second calculate a value for the point of inflection at 5/3. There's your negative 0.59 output, which we had rounded to negative 0.6. Okay, but use your calculator to just check and make sure that your work makes sense. Whoops. Okay. Any questions?